Hello everyone, welcome to MI Tech Institute YouTube channel. In the previous class, we have discussed about some basics of electromagnetism and what is meant by electromagnetic flux and magnetic flux density and some terminology related to the magnetic field. At the same time, we have discussed about the forces. When the current carrying conductor is straight wire, in that case what is the direction of magnetic field, and the fourth direction also we have discussed in the previous class. Today class we will discuss about electromagnetic induction. First of all, what is meant by electromagnetic induction? Let us see. To understand this electromagnetic induction, both the Faraday, scientist known as Faraday, and Henry, they have carried out some experiments, and finally they have concluded that now when you keep a coil, a circular coil, this is a circular coil, it is connected to galvanometer. Now when it is connected to the galvanometer, in that galvanometer, whenever there is no magnet near to this galvanometer, then the deflection in the galvanometer is null. That is, it haven't shown any deflection in the galvanometer. But when you bring a bar magnet which is of north pole, consists of a north pole and south pole, when you bring this bar magnet near to the coil, then what is going to happen? You know that bar magnet consists of some magnetic field lines. These magnetic field lines are keep on changing as the bar magnet moves towards the coil. The change in magnetic field lines, in a coil is called as a magnetic flux. Now the change in magnetic flux will produce some current in this coil. That current is called as a induced current. Once again I am telling, now when you bring a bar magnet near to a coil, now this bar magnet produce some magnetic flux change in this coil. The change in magnetic flux will induce some current. That current is called as a induced current. This law is known as a electromagnetic induction. Now in that, first of all, the magnet is moving, the coil is in the fixed position. Second time, the magnet may be in the fixed position, the coil may be in the motion, or third case, the both may be in the relative motion. Now in this one, when you bring the bar magnet near to the coil, the change in flux will produce some deflection in the coil. For example, assume it is in the towards the left y direction. For suppose if you bring this bar magnet somewhat away, now in this case it will produce the magnetic flux, okay, in the opposite direction. Therefore current also changes in the opposite direction. Next one is Faraday's law. See, whenever there is a continuous change of magnetic flux linked with a closed coil, a current is generated in the coil. This law is called as a Faraday's law. In that, whatever the induced EMF generated in the coil, that is equal to the magnetic flux rate. If the magnetic flux are more, then the induced EMF is also more. Now this induced EMF is equal to change in flux by time. Now see, previously we found the flux for only a single coil. Now if you take some n number of coils, okay, now if for example, there is a case where we use a n number of coils. In that, the flux we already discussed in the previous class, the flux symbol will be pi. The number of coils, okay, now it is each having some n turns. Therefore, the n into pi will be equal to the total number of turns in a coil. Therefore, finally we will get the EMF formula. So the EMF is equal to n into pi naught into delta t. Pi naught is that flux of each and individual wire, and we like that we are having the n terms. Now this Faraday law has given the given the magnitude of EMF or the induced current, but it not explained about the direction of current. Now this will be explained by a law called as a Lenz law. Let us see what Lenz law explains. Now this law gives the direction of induced EMF and the current in a coil. Now see what we are doing here in this activity. Now we are taking a coil. Okay, now that is called as a solenoid. We are taking a coil of n turns. Now this is connected to a galvanometer. Now you know what is the function of a galvanometer. Okay, now if there is any change in the current, it will show some deflections in the galvanometer. Now see, whenever you bring the north pole of a bar magnet near to the coil, now what is going to happen? As a change in flux in the coil will produce a current. That current will be flowing in such a manner that current carrying conductor will also behave as a bar magnet. Like that, this is behaving like a bar magnet of north pole and south pole. Now the north pole of a bar magnet and whatever the magnetic field produced by the current, that will also behaves like a magnet. Therefore it is also having, for example, the north pole is this side and south pole is this side. Now when you bring these two near to one, what is going to happen? There is some repulsion force is going to happen. And sir, no, now north pole and north pole both are there. They are going to repel each other. As they are going to repel each other, Now this is the direction of the force which is going to act in this direction. Now I am keeping my thumb in the direction of the force. The curling finger will indicate the direction of current. See, as I am moving this towards the left in the direction of force, this curling fingers will indicate the direction of current. Therefore, if you see that curling fingers, we are getting a direction called as in a anti-clockwise direction. Similarly, if you move this bar magnet away, then what is going to happen? The number of field lines passing through this coil is also changing. The magnetic flux will be in the reverse direction, cause the current into reverse manner. Therefore, this will become as a south pole, this will become as a north pole. Therefore, the magnet will be attracted towards it, like the forces are attracted towards it, or the current direction is reversed. The change in current direction, previously it is in anti-clockwise direction, now it will become as a clockwise direction. Okay, now just we have to remember that when you bring a bar magnet north pole near to the coil, the current produced in the coil will be like anti-clockwise direction, and if you move away or if you bring the south pole of this bar magnet near to it, the current direction will be clockwise direction. This point you have to remember. Now see the definition of Lenz law. What Lenz law has explained. The direction of induced current is always so as to oppose the change which causes the current. This is called as a Lenz law. Now let us see some applications of Faraday's law of electromagnetism. See what the applications we are having. Now first one, it is used in the security checkups. The Faraday's law is used in the security checkup. Let us see how it is used in the security checkup. For example, you consider whenever you go to some functions or at shopping malls, there you can observe this kind of security checkup. At the same time, whenever some VIPs are coming, okay, in that case for the security purpose they will check with this like a bat-like structure, like the circular coil-like structure. Now see in this one, if there is any metal object is there, we will get the sound. Let us see how this sound is going to produce in this one. Now see what they are doing means, first of all, in this one they will supply the AC current. Okay, now throughout this one they will supply the AC current along this one. Now when you know that whenever a current carrying conductor is there, this current carrying conductor will produce a magnetic field. Therefore it can produce a magnetic field like this. Just assume the magnetic fields are like this. Now when you keep a metal object in this one, in this magnetic fields, what is going to happen? It will disturb the magnetic field. Now the disturbance of magnetic fields will produce a magnetic flux. Yes or no? The disturbance of magnetic field will produce a magnetic flux. The change in magnetic flux, according to Faraday's law of induction, it will produce a current. Now whatever the current we are producing, that current is supplied to the bell. Therefore here electrical energy is converting it as a sound energy. Okay, now electrical energy converting it as a sound energy, then we can then the bell will ring. Okay, now when you carry a metal object. Similarly here also what is going to happen? Similarly we will also supply here AC current. Now whenever you supply AC current in a coil, the AC current in a coil produces a magnetic field. Now when the metal object is detected by this magnetic field, or whenever you keep a metal object in this magnetic field, the disturbance created by the metal object will create a magnetic flux in this one, the change in magnetic flux. The change in magnetic flux, again they will convert it as a electric energy, that is called as a current. That current energy is converting it as a sound energy. In this case, that metal objects will be detected by the security checkups. Now next one, in the tape recorder. Now this application is also used in the tape recorder. Let us see what is the application they have used in the tape recorder. For example, consider we are having the tape recorder two parts. One is called as a tape recorder head, another one is called as a cassette. You know, in the olden days we will be having a cassette like this, and there will be some reel on this one. Like this, it will continuously move from one side to the other side after completion of this one. Now see, in this one, first of all, we are giving a current supply, that is electric supply in this one. Therefore the current is passing through this circuit. Now when the current is passing through this one, this current will be produce some magnetic field, right? This magnetic field is produced in the tape recorder. Now whenever we keep the cassette, on the cassette some reel-like structure will be there. It is coated with Fe2O3 metal coating. Understand? Fe2O3, like Fe is a metal. Therefore whenever you keep the cassette in this one, therefore this metal, whatever the coating is there, that metal coating will be create some disturbance in the magnetic field produced in the tape recorder. Therefore this change in magnetic flux produce a current. Okay, now produce a current. That current is amplified. The current is amplified and behaves like a sound. Now that will be sent to the sound box or the speaker. There we will get the sound of whatever the songs or something music is there in this cassette. This is about the working of cassette. Next one. Third one is ATM machine. In the ATM machine also we will use the applications of Faraday's. Let us see. In ATM card we are having in ATM machine we will be having there is a device in which we will insert some ATM card. Another one is the ATM card, and backside of ATM card it will be coated with the magnetic strip. Now when you keep this ATM card with some magnetic strip in this inserting part of a ATM machine, then this will behave like a bar magnet. Which one? ATM card will behave like a bar magnet. When you keep this one in this one, it will behave like a bar magnet, therefore it will produce a magnetic flux. Okay, it will change the magnetic flux. Now whenever the change in magnetic flux is produced in the machine, that will be amplified and converted it as a binary conversion like zeros and one. Why? Because the machines can understand only a binary language which is of zeros and ones. Therefore whenever you this machine, whatever your ATM card you kept in this machine, it is converting it as zeros and one. It will send the signals to the whatever the data it is there in the system. Therefore whatever the data of our ATM card will be displayed on the screen. That may be your name, your mobile number, your account number, or your balance, something else, everything, the data which is stored in this magnetic strip, that will be displayed on the computer. Here also the change in magnetic field create a magnetic flux. The change in magnetic flux will produce a current. That current is amplified or converted as a 0 and 1s of a binary conversion, and after that it is displaying our data on the screen. This is about the third one, ATM machine. Next, last application is called as electromagnetic induction. Last application is electromagnetic induction. Let us see where we use this electromagnetic induction application. In nowadays, within a short period of time, to heat some objects we are using the induction stove. Let us see what is happening in the induction stove. Now induction stove consists of one surface. Below the surface there will be one coil. Below the surface of induction stove there will be one coil. Now whenever you give the electrical energy, like whenever you switch on this coil, the current is going to pass through this coil. Now when the current is going to pass through this coil, you know that current carrying conductor will produce a magnetic field. That magnetic fields, whenever the magnetic fields are produced in this coil, now on the pan or like on the surface of this induction stove we will keep a metal pan. Now whenever you keep a metal pan, now magnetic field produced by this one, that will be disturbed by this metal pan, and that will produce some electrical signals or electrical current is going to produce. That current is converting it as heat energy. Electrical energy is converting it as a heat energy. The best example is water heater. Okay, the best example is water heater. Now water heater, when you switch on, that electrical energy of that whatever we are having, that will convert it as a heat energy. Like this we will use the electromagnetic induction in these applications. Thank you.